Welcome back to Structural Dynamics. Today in this lecture we are going to discuss regarding the free vibrations with viscous damping. We have seen derivation for free vibration with viscous damping. In this lecture we will see how these free vibrations with viscous damping vary under the condition of underdamped system, critically damped system and overdamped system. What are these systems are? Okay, we will see one by one by using this particular dynamic equation. In the previous lecture we have seen free vibration with viscous damping and we have gone through the derivation for this particular single degree of freedom system, which is connected with the spring stiffness parameter and uh, damping constant, okay, damping parameter. By using this one we have found two roots of that particular equation, ordinary differential equation, and by using these two roots of the equation we have converted these two equations in terms of the x of t is equal to c1 e to the power of s1 t plus c2 into e to the power of s2 of t. Displacement parameter, we have converted this one in terms of the displacement parameter. We have only single degree of freedom system. That single degree of freedom is nothing but x of t. That one we have found, we are finding by using this equation, and this equation finally we used to get in this particular form. Okay, by depending on we can see here two different real roots we can see here, and by using those two different real roots we can formulate this displacement equation, whereas c1 and c2 are the arbitrary constants to be determined. And after that we have seen to convert the ratio of the we have taken a ratio of c to cc, which is nothing but cc is the critical damping that is taken by the material or any structure, the maximum damping of that particular structure, whereas the c, the amount of damping required to diminish the waves, to reduce the amplitude of the waves. Okay, to reduce the amplitude of the waves, this particular damping is sufficient. Okay, whereas structure will have the maximum cc, critical damping, okay, maximum capacity of the that particular structure. Ratio of these two we have taken as the zeta as the damping ratio, zeta parameter. Okay, and by using this one we have substituted all these parameters in the equation which we got from 6 and 7, and from there we have seen here frequency dependent parameter minus zeta plus or minus under root of zeta square minus 1 into omega n, whereas these two roots can be converted into this form, and final displacement equation we got like this: c1 epsilon into minus zeta plus under root of zeta square minus 1 into omega n into t plus c2 into epsilon into second root s2, where I have second root is having the minus n into omega n into t. Okay, by using this equation, this displacement equation, we used to solve problems for underdamped system, critically damped system and overdamped system. Here we can see the case 1, underdamped system. Okay, underdamped system for free vibration of single degree of freedom system with damping condition. Okay, when we provide damping, after providing the damping we used to go for three cases. Case 1 is underdamped system, means the ratio of c by cc should be less than 1. Okay, that ratio zeta is less than 1, whereas c is lesser than the cc. Okay, c is less than the cc, then we can get zeta is less than 1. Okay, for this condition what we used to do, we used to convert this particular value zeta square minus 1 is negative, we used to take this one as negative, minus 1 is negative, and the roots s1 and s2 can be expressed as like this: s1 comma 2, both any one root s1 and s2 is equal to minus zeta plus or minus what we used to do here. Here we used to take minus as common. For that minus we used to take as complex number I outside I square, and that I square we used to take outside, then it will becomes I under root of 1 minus zeta square into omega 1. Okay, if you take zeta is less than 1, we used to use this condition. Okay, and why we have taken this one? If we take zeta is less than 1, means zeta square also will becomes lesser than this particular value. That's why what we used to do, we used to take from this equation, in place of zeta square minus 1, we used to take minus 1 as common. We used to make to satisfy this condition. After satisfying that condition, we used to take these two roots, and these two roots can be written as like this. Okay, we can see the equation like this. From equation 8 can be written as this. Equation 8 can be written as like this in this particular form. Okay, we can get x of t is equal to c1 epsilon exponential of minus zeta plus I under root of 1 minus zeta square into omega n into t is the first term, plus second constant c2 into epsilon into minus zeta minus I under root of 1 minus zeta square into omega n t. Okay, this is the displacement equation. Okay, after this what we have to do here, we have taken minus zeta into omega n t has been taken as the common here. Okay, it is common for both the parameters. Omega n and t is common for both parameters, and minus zeta is also common for both the parameters. That's why we have taken like this. And intermediate terms, exponential term of c1 is constant is there, e is there, and another parameter I under root of minus 1 zeta square is there, omega n into t, and c2 into zeta epsilon minus I under root of minus zeta square into omega n into t. For these two equations we have written cos format. For complex numbers we used to take roots like this. If you solve this equation, you can get final equation like epsilon minus zeta omega n t into c1 plus c2 as common. We used to take first terms are I under root first terms we used to take cos under root of 1 minus zeta square into omega n into t for both cases, c1 and c2. Two parameters we used to get. If you take c1 plus c2 as common, then we can get this one. Sorry, cos under root of 1 minus omega square into omega n into t. If you take this one as common, then we used to get c1 plus c2. Similarly, for imaginary part also we used to take equation like this. Okay, these are the two equations we can get from this underdamped system. Okay, from that equation we can write here x of t is equal to epsilon exponential of minus zeta omega nt into c1 dash cos under root of 1 minus zeta square into omega nt plus c2 dash sin of under root of 1 minus zeta square into omega n into t. We have taken this equation, whereas c1 dash and c2 dash indicates c1 is nothing but c1 plus c2, c2 indicates c1 minus c2. These two parameters we keep remaining. We used to find those two parameters as c1 dash and c2 dash. Okay, after finding this one is the equation we used to format. And after getting this displacement equation, here for the initial boundary condition we have some boundary condition, initial condition at the starting t is equal to 0, displacement is equal to x naught, and at t is equal to 0, velocity also will become 0. Sorry, x naught dot okay, dx naught by dx dt. Okay, there we can get velocity also, initial velocity also like this. If you substitute these two parameters in the above equation, this particular equation, from this equation, if you solve this equation by substituting these two boundary conditions, we can get c1 dash as x naught and c2 dash as x naught dot plus zeta x naught omega n by under root of 1 minus zeta square omega n. Okay, this complete equation we can get after substituting these two boundary conditions. Okay, if you substitute these values in this particular equation, above equation, you can get the equation 9. And this equation is called equation of motion for damped condition for the first case underdamped system. Why we are providing underdamped? Underdamped means damping coming from the waves is very lesser than the critical damping provided to the structure. Okay, that's why we used to say this one as underdamped system. And we can get the equation 9 by substituting all these boundary conditions. This is regarding underdamped system, and if you see here, the motion described by the equation 9 is a damped harmonic motion of the angular frequency 1 minus zeta square into omega n. Okay, whereas this theta angle between angles provided here, these two angles we used to take as angular frequencies. Okay, but because of the factor epsilon of minus zeta omega mt, the amplitude decreases exponentially with time. Okay, because of exponential function here we are going to use, and because of this function there is a lot of decrease in the amplitude. It will decrease in exponential way. The quantity can be described by using the frequent like WD. Okay, where this WD is nothing but undamped natural frequency. This is WD we used to use for the undamped underdamped natural frequency condition. Whereas we can say omega d is nothing but frequency of damped vibration. Frequency of damped vibration, we can say this omega d. It can be seen that the frequency of the damped vibration WD is always less than the undamped natural frequency omega n. Frequency of damped vibration is less than the natural frequency of the wave. Okay. The decrease in frequency of the damped vibration with increasing amount of damping given by the equation 10 can be drawn diagram like this. Okay, it will be, if you see here diagram, this particular, if you substitute these values, frequency values, you can get the ratio of omega d by omega n as like this. Up to maximum damping we can use, sorry, damping will be less than 1. Okay, zeta will be less than 1. Up to that point, WD by WN ratio can be, we can see like this. This is regarding underdamped system. And if you see the diagram, here we can see one diagram, whereas damping has been started somewhere with pi phase angle pi, and it has been recorded like this, and it has two different amplitudes, x1, x2, x. You can see amplitudes here. The maximum amplitudes are there, and at particular distance, if you take t1 at t2 and t3, if you take like that, at every point the amplitude of the wave has been decreased. Okay, from here to here there is this one is decreasing, and here to here also wave is decreasing. If you see consecutive amplitudes, vibrations, there will be reduction in the waves. And how they are reducing this function, these waves are reducing. If you join all the amplitude parameters, peak amplitudes, you can see here exponential way of decrease in amplitudes. Okay, and that exponential way of decrease we can indicate with the parameter x into epsilon into minus zeta into omega n into t. The exponential indicates the exponential decrease of wave, whereas minus indicates the decrease of parameter. And the time period we can take td, dynamic time period, we used to take as 2 pi by omega d, damped frequency we use here, and damped time period. Okay, this is for diagram for underdamped system. Pi naught is the initial phase angle, t1 is the time periods, consecutive waves we can see here. With this I am stopping here underdamped system. Please subscribe my channel, my YouTube channel, uh, CE Masters. Thank you for watching.